Totient function, since some student asked, let me just go over that again. So it is number of relative integers that are relatively prime to n. Important is relative to prime, which means it doesn't have a common factor with it. Let's go by example, see what it exactly means. So if you say we want to find total 18, so n is 18. So how many of them are there? Okay, let's see how many of them are there. So then 18, so the number is 18, so n is 18, so 1 is relatively prime. And then you will have 2, no, not 2, 3, right? So 4, no, it's divisible by 2, and 5, and 7, definitely, 6, no, 8, no, 9, no, divided by 3, 10 divided by 2, 11 is one of them, and then 13, and then 17, 14, no, 15, 16, and then 17. So don't have all these numbers don't have the prime number, but in this case it happen to be prime number as well. Sometimes you get confused. So how many number of there? So 1, 2, 3, 4, 5, 6, 7, 6, not 3. So no 3. So there are 6 of them. So it equals 6. So 6 of them. Okay, let's do another one. So you can find, let's go 25. So how many are there? Let's do the same thing. So just try to be good at it. So 1, 2, 3, 4. Okay, don't have to be prime number as long as it's relative to prime to 25. It is okay. So then 6, okay, and 7, 8 is relative to prime to 25. 9, 10, not 11, 12, 13, 14, realizing as long as it's relative to 16, 17, 18, 19, 20, no, not 20, because 20 is divisible by 5, and not 20, okay, no 20, let me put it, no 20, and 21, okay, and 22, and 23, and 24. All these numbers below 25 are relatively prime to 25. So how many of them? There are, if you count them up, there are totally 20 numbers. So we will say, so there are 20 numbers. Let me put a color. So there are, so it's 6, there are 20 numbers. So these are 20 numbers. So now, so it's kind of tedious to find out. But then if you now, I'm not finding the prime number, so find the numbers that are relative to prime to 25. So there are 20 of them. So there's 5 of 25 is 20. So in fact, there are online software that does this, so you can try. But now for a relatively larger number, like 78, it would take a while. For example, let me give a try. So how about 1 and 5? Get 2 is not, and then 7. Maybe I missed it, and 9. Okay, so there are many. You can just try as long as, let's say, X is among the list. So GCD of X and 79 equal 1, co-prime to 78. So that all qualify. How many of them are there? Well, it takes a while for you to find out. So that is actually 24 of them. Okay, I'm not going to go over. I will challenge you to do that by hand. The point I want to find out is if the number is large, say like you have 714, okay, it will be very difficult to find out by hand, but you can if you have computers. But if it's a huge number and you're not going through, but you can still do it. But then, in fact, this is the fact. That's why RSA later on you will learn. Based on this fact, you find the totient. If you just find the totient by hand, it's very hard. Okay, and almost impossible if the number is large. So now we have some theorem properties. Now, so just that's what the totient means. Relatively prime to a number. How many are there? So now let's see. There is something simple. If this is a prime number, so this relatively becomes easy. Prime number is not divisible by anything. So basically, the totient is a freedom prime number. I have a prime number, let's say 11. So how many of them are relative to prime? Well, any number that below it is relative to prime. Say 1, 2, 3, 4, all the way to 10. So a relative to prime, co-prime to 11. So there are 10 of them. So how about 13? So they are all the way to 12. Therefore, for a prime number, totient is easy to find. It's nothing but if it's a prime number 11, so it's equal to 10. So prime number, say 13, that will be 12. Because anything that below is relative to prime. So therefore, primary number equal to p and minus 1. 4. So this is the important factor to remember. To calculate the totient, if it is a prime number, it's very easy. Note that we want to calculate the totient, which is the primary number, the number of primary numbers that are relative to prime to n. So the reason we want to do this calculation is that later we're going to use this property to do the RSA encryption and things. So now, we want to find all the possibilities of calculating things easily. So here's another theorem we can use. So if a number is a multi-product of two numbers that are relatively prime, so m times m. If this is the number can break up in multiplication, and m and n are relatively prime, and then remember, they don't have to be prime. Okay, they are relatively prime. So a will be equal to this. Okay, well, you can think about the product rule. That's not the formal way to talk about it. So you can do m and n co-prime, which means, for example, 25 and 9 are co-prime, even though both of them are, neither of them are prime numbers. So then you can do 25, and then, so it's like, you can do this whole, this is very important. Let me put it in the square. So this property. So m and n just have to be co-prime. So then we have this one, and this one. So then we can use this property to compute the number, totient of some number that's relatively large. Once again, what is the totient here? Is this function. That's the number of positive integers that is less than and relatively co-prime to that number. So we have the examples here. Now, for calculating totient, we have two theorems or properties we can use. One is that if the two numbers are relatively prime, but then is m and n are multiplied prime, then totient, you have this product rule, and you can multiply this. Note, m and n themselves don't have to be prime, but they have to be co-prime. M and m co-prime, or relatively prime. And that's this. Remember, co-prime, okay? So that's one thing. Another thing is what we said is if p equals a prime number, totient is simply equal to p minus 1. So that's what the totient is defined. Then we have another property. Combine these two. If a number n is actually equal to, of course, this n is not an n above, p P times Q, where P and Q are the prime numbers, but they are not equal to each other. So not equal to each other. Okay, without prime numbers, they're obviously relative prime as well. Therefore, you will see here relative prime, and then you will say P minus 1 times Q minus 1. So we use both of them from the above. We derive this. So this is what we're going to use. Note, P must not equal to Q. I'll ask you to prove later on. So this is the property we can use. So to calculate a large prime number, because think about it, if you calculate this, just around some number like this huge number, it's almost impossible to calculate this by hand. Or you can calculate even by computer if a large number will take a long time to calculate totient. But we need a totient to get the primary key to break it. So now, but only in a special case if this is break down to some number P times Q, if possible, then the calculation of this is simple. So if you can computer, you know it's very easy to do a multiplication of two numbers. But if you want to refactor out what the reverse process is, very hard. If I multiply two prime numbers, I give you the products, then it's very hard to reverse it back if the number is large. Okay, even a small number, it will take a while for you to figure out what are the two prime factors. So that is really the fact that the hardness is that what this RSA encryption is based on. The reverse process is very challenging. You cannot just figure out the primary key. So now here, let me give you an example. We're using this. So now these conditions are very important. P and Q are prime numbers. Okay, so now let's find an example. Q. Let's do our earlier homework. So this is 90. So if I want to figure out that, like by hand, you can find a couple of them. How many of them there? Say 1 is them. Say 5. No, 5 is not. How about 7 maybe? 17 maybe. So how many of them there is very hard to find out. So now we can recognize that this is equal to 2 times 45. So realizing they don't have the prime number at this stage, but we just use the theorem 1. So if they are relatively prime, so relatively prime, so it's equal to this. 2 and 45 are relatively prime. 45. Okay, 45. So now 2 is a prime number, therefore that's just 1, because 2 minus 1 is 1. So times this. So this we can further break down into two relatively prime numbers. So then 1 times, then what again? 5 times 9 is 45. So that's 5 and 9 are relatively prime, even though 9 is not even a prime number. But you can do this, so therefore it's equal to this and times 9. So relatively prime, 5 and 9 relatively prime. So then 5 itself is a prime number, therefore 1 times that is 5 minus 1 is 4, but then this. Okay, so then there, be careful. So now you have to find, so that's a 4, 1 times 4. So now you realize that 9 equals 3 times 3. But here is the trap. So our theorem says they both have prime numbers, but they have to be not equal. Okay, they have not equal. So then if you're not equal, so then you cannot use this theorem. Okay, it's not equal, and this should be coprime. It's not coprime, not equal, and not coprime. So 3 and 3 not coprime. So therefore you cannot use this. So in other words, this 9, totient 9, is not equal to totient 3 and totient 3 squared. So which is actually, in fact, on this side is 4. It is not equal 4. So because why? What we have above is that everything must be valid. So you have this. So let me change the color. Since this is important, this is what we're based on. Very hard to change the color. Okay, I circled out what we based on, the properties or the propositions. So now we have to directly calculate 9. So if you count how many of the numbers that are co-prime to 9 below 9, let's see that we'll do the by hand again. So let me find a place here that 9. So how many of them are there? So if you see, okay, put them together, 1, 2, 3 is not, 4, even though it's not a prime number, okay, 5, 6 is not, 7, and 8. So any more? So 1, 2, relatively to prime 9, there are 6 numbers, so therefore equals 6. So therefore it's 6, not 4, okay? So not 4. So therefore 4 times 6 is 24. So you have 24. So then you will see that when you can break up this number 90 into the multiplication of two numbers, or if you can break up into the primary numbers like this, the totient is just a multiplication away. So that's the reason. The reason we want to do that is that when you do the encryption, you need to calculate totient of a large number. But then we have n equal a large number. But now, if you want to do encryption, you will need this totient. But if I just give you the n, then I give you the public key, you cannot calculate the private key because you don't know what this totient is, n. So you remember you need this to calculate, but only you will know, say, 5, 27, and so on. But then how you break up? It's very hard to break up. An easy number, you can break into 2, you just multiply them, you get the totient. But if it's a large number, it's very hard. In fact, the hardness, the safety of the RSA is based on that the interceptor or the attacker have very difficult time to figure out what are these two factors. So if he wants to calculate the totient, you're going to give him the large number, he can't find the totient. Because you have to break a large number to two prime factors. He doesn't know the two prime factors. He doesn't know anything. So that's the whole thing about it. And that's the reason we want to learn all this. All right. Hope this is helpful. Bye for now.